Okay, so there are basically two more things that I want to show you, and one of them is how one can go beyond what we have seen. So remember that the starting point of our of this whole business about logarithmic Sobolev inequalities was that we could look at the entropy of a random variable, which is just the expected value. The expected value of this function phi of a non-negative random variable minus phi times the phi of the expected value. See, where this is the entropy when phi of x is x log x, then this is bounded by the expected value of the sum of the conditional entropies. So the expected value only with respect to the ith component of phi of z minus phi of the expected value only with respect to the ith component of z. Right? This is what we called the subadditivity of entropy. Okay? But when we take phi of x equals x squared, then this is also true, and that's the Efronstein inequality. Okay? So you may wonder, are there some other functions for which this may be true? And if there are, can we do something with them? Something meaningful that we cannot do with these? And the answer is yes. So we can define the phi entropy. So for some function phi defined on the non-negative numbers, we can define the entropy exactly the same way as before. And it turns out that this subadditivity property, which is what I just wrote here, it's written with a slightly different notation here, but this property is true not only for these two functions, but for a whole class of functions. And what you can actually characterize for what kind of functions phi this is true. Well, they have to be twice differentiable, and either they are linear, or 1 over the second derivative should be concave. It's not clear intuitively what this means, but these two functions are in there. So when phi of x is x squared, then this is just the Efronstein inequality. When phi of x is x log x, then this is the subadditivity of entropy. Another whole class of functions that you may try is x to the p. Right? And if you check these assumptions, it turns out that this will hold whenever t is strictly greater than 1 and less than or equal to 2. So Efronstein is somehow an extremal case of this. But maybe other values of p are closer to 1 are also meaningful. This x log x is a little bit like something to the left end. So it feels like these two examples are somehow extreme. Okay? So in particular, one can start working with phi entropies of this type, but maybe some other phi entropies will also work. I have no idea. It would be very nice if it did. But with this, you can actually go quite far. And so let's look at this random variable, v plus. Okay, so what's v plus? This is our usual, the Efronstein estimate of the variance would be the expected value of v plus. This is a random variable. Before we had we had inequalities that said that if this is bounded by a constant, then we have a sub-Gaussian. If this random variable is bounded by a linear function of z, then we have something like a Bernstein type of inequality. Well, this is a random variable. Okay? Now, I don't want to put any conditions on this. And one can show this kind of inequality, which is not clear at the first sight what it says, but it's somehow a generalized version of the Efronstein inequality. It involves, what it says is that the qth moment of z minus EC. No, I only look at the positive part because I want to prove inequalities for what's the probability that z is greater than its expected value by more than t. And if I do this, one way of using Markov's inequality is that I look at z minus Ez, the positive part, to the power of q divided by t to the power of q. Right? Now, what this says that for this qth moment of this random variable can be bounded by something which is alpha is less than q minus 1. So this is a lower moment of the same random variable. And here we have this guy, v plus, and z minus Ez to an even smaller power. Okay? So for example, if v plus is bounded by a constant, then this constant comes outside, and I have an inequality for the qth moment, which involves the, let's say if I use it with alpha equals q minus 1, this is the q minus 1 first moment, and this is the q minus second moment. So now I can bound the qth moment of my random variable in terms of lower moments. So this calls for recursive arguments. Okay? So what we get here is instead of differential inequalities, we get somehow recursions, difference inequalities. So if you work out the details, then this is a kind of inequality that you can get. So the qth moment of this random variable, and now I just take the 1 over qth powers, but it doesn't matter. So the qth moment of this can be bounded in terms of the q halves moment of this random variable v, of this guy here. Okay? So what this inequality says is that if I can somehow control this guy v here, then I can say something about moments. Okay? So in particular, if this random variable is bounded by a constant, right? That was our bounded differences assumption. If this is always bounded by a constant, then this is just a constant here, and what we get is that the qth moment, raised to the power 1 over q, is less than a constant times square root of q. Well, that's just a sub-Gaussian behavior. So you can show that if you have something like this, if the tails behave like e to the minus t squared divided by v, then what this means is that the moments, the expected value of z minus Ez to the power of q raised to the power of 1 over q will be less than something like a constant times, and here we have v square root of v. And these two are basically equivalent. You can go, if you have a random variable that is sub-Gaussian in this sense, then the moments times square root of q. Then the moments grow like square root of q, and vice versa. If you have moments like square root of q, then you can use Markov's inequality to prove sub-Gaussian tailwinds. So what this says is that if the moment, the growth of the moment, that somehow characterizes the tail behavior. If it goes like square root of q, the qth moments raised to the power 1 over q grow like square root of q, that means sub-Gaussian. If the moments grow like q much faster, then it's like sub-exponential tails. If the moments grow like q squared or something bigger, then you have even heavier tails. Okay? So how fast the moments grow, that give us the tail behavior. Okay? So what this inequality says is that we can go way beyond of what we have done before, because now all we need to do is to study this random variable here. Okay? And then you may be able to say something about the moments of this random variable. Okay? And if you can do that, then you can use this inequality to get moment bounds. In particular, here you don't really need all those boundedness assumptions that we we always needed it in the previous language. Okay? Now this gives us a way of handling unbounded increments. For example, suprema of empirical processes with unbounded increments, you can use this inequalities. Yes?
Also in this case, if our function is affine, then we only require qwise independence among the random variables.
If our function is
affine or linear, you would require only qwise independence among the xi's.
Oh, yes, but okay. To get bounds for the qth moment. Yes, that is true. Yeah. Yes. Well, yeah. Okay. Yeah. But this is typically not for linear functions. This is typically for if you want to there's actually a whole research area which is they're trying to prove concentration bounds for not functions of not completely independent, but maybe partially independent random variables, and the function is they're typically linear or something similar. And then that's another whole world. Okay, and to finish, I want to show you something which I find absolutely fascinating, and it has these are not completely. Well, not exactly concentration inequalities, but in spirit, it's very, very close to what I have been telling you about, and I find it absolutely beautiful. This kind of stuff has been used also in learning theory in some ways. So let me tell you what this is about. So now from now on, our space is the hypercube. Okay, so we are in the n-dimensional binary hypercube. And we take a uniform vector in this. Okay? So now X has independent components, and they are all plus minus 1 symmetric Rademacher random variables. Now, and we are asking whether this we look at now a subset of the hypercube. Okay? And we want to know whether this X is in this set or not. Now, the influence of the ith variable is defined as the probability that if I change the ith variable, then I go in and out of the circle. Okay? So I take now n independent coin flips, and I'm looking at what happens if I fix everything, and I look at what happens if I flip one component. Okay? If I go in and out of the set by flipping this component, that's an event. Right? And now I take the probability with respect to all other random draws that this event happens. Right? That I go in and out. That the ith variable is influential. Right? You can think about this as, for example, in voting theory, this has been used a lot. Right? So maybe we vote for something. We want to choose from two candidates, and everybody has a vote. So these are the x1, xn, and we have some complicated voting scheme. Right? You can come up with any voting scheme you like. Majority vote is one example, but maybe I decide. That's another a little bit less democratic voting scheme, or maybe there are 5 of us who decide somehow. So you can think about any way of it, right? If the set A is just the set of outcomes for which candidate number 1 wins. Okay. Now I want to look at what's the probability that your vote decides. Yeah? That if you change your vote, then the outcome changes. That's the influence of the ith variable. Okay? If you change your vote, then the whole outcome becomes different. Okay? So this is called the influence of the ith variable, and the total influence is just the sum of the influences. Okay? Now we sum all these numbers. All right. So dictatorship would be when I decide. So that means that A is the set of all those x's when the first component equals 1. Okay? So what's the total influence of this set? Well, I sub 1 equals 1, right? Because my decision is for sure influential and nobody else matters. So the total influence here equals 1. That's dictatorship. Okay? Is this clear? Parity function. Right? This is a strange voting rule. We say the candidate number 1 wins if the total number of votes is even. Okay? That's a strange rule, but we can calculate. Now everybody is influential. So this is a good democratic voting system. Right? Everybody has complete control. The total influence is n. Okay? Problem with this is this is not a monotone rule. Right? We would like to have monotone voting systems. So if anybody changes his vote from number 2, candidate number 2 to candidate number 1, and nobody else changes, then this should only help candidate number 1. Well, with parity, this is not the case, but with majority, it's the case. Okay? So with majority, this means just that we count the number of votes, and if it's greater than the threshold, let's say at least half of them should say candidate number 1, then candidate number 1 wins. What's the influence of a variable? Well, a variable is influential exactly when the sum of the variables equals 0. Okay? This is a binomial random variable. What's the probability that a symmetric binomial is exactly half of the equals n half? Well, that's something like square root of n. 1 over square root of n. So the total influence is n times 1 over square root of n, which is about square root of n. Okay? Now, the Efron-Stein inequality, this influence is something like, it's familiar, right? But what happens, probably that we change one variable. So the total influence is what comes up in the Efron-Stein inequality when we use it for the indicator function of this set. So the Efron-Stein inequality tells us that the probability that the variance of the indicator function is less than the Efron-Stein estimate, which is just the influence divided by 4 in this case. Okay? So this shows that the dictatorship is the set that has the smallest possible. So let's say we restrict ourselves to sets that have probability 1/2, then dictatorship is the one that minimizes the total influence. Right? Because for the dictatorship function, this is 1/2, so this is 1/4. So what this says is that the influence is always at least 1, and the dictatorship it equals 1. So Efron-Stein tells us that the dictatorship has the minimum possible influence. Okay? Now the maximum possible influence this is the parity function, clearly, right? Because the influence can never be larger than 1. Everybody has that maximum influence. And you can also show that if you restrict yourself to monotone sets, then majority function has the maximum possible influence. Okay? This is a classical result from it's an isoperimetric result in the graph theory. Why is it an isoperimetric result? Because what's the total influence? If we have a point which is in the set, right, then we want to look at how many variables. If you count this in a different way, then you just count how many edges lead out from this set. So the influence is basically if you have a set A, and now you look at the complement of A, and you count how many edges are there between these two sets. So you look at the hypercube now as a graph, okay? And we count how many ways can we go in between these two. Okay? So the total influence is just the number of edges divided by 2. Okay? So, and it's known what's the monotone set that has the smallest number of edges going on. That's just the majority. This is called the Hamming ball. Okay. All right. Now, instead of the Efron-Stein inequality, we can try what happens if we use the logarithmic Sobolev inequality. something that was useful in concentration, so we can try it. So if we do that, then you get this inequality. Okay? It's really easy. So you just use the Bernoulli. Remember, the Bernoulli logarithmic Sobolev inequality told us that the entropy, this guy, using phi of x equals x log x, this thing is bounded by the Efron-Stein estimate of the variance, right? The sum of z minus zi prime squared. And maybe there was a 1/2. Okay? This was the Bernoulli logarithmic Sobolev inequality, so we can just use it here. This is the total influence. So we have something that has the entropy is related to the total influence. And this is what you get after massaging. Okay? So one corollary of this is a very, very famous result of Kahn-Kalain lineal. They actually proved it using completely different techniques. They used it. They proved it using Fourier analysis in the cube, using deep results from harmonic analysis. But what you get from this for free is that no matter what A is, there is an influential variable. Let's say, again, think about sets that have probability 1/2. Then what we have here is a constant. This is 1/4. And here we have log n over n. So what this inequality tells you is that no matter what the set is, there's always a variable whose influence is at least log n over n. Okay. In particular, if we have a set which is a democratic set in the sense that everybody has the same influence, this is a very general assumption, it's a very weak symmetry assumption, then this implies that the total influence is greater than log n. So for all functions that are symmetric in this very weak sense, the influence is at least log n. So let's come back here. You see, this is, of course, not everybody has the same influence here. This is a constant. The majority function has an influence which is much bigger. It has root n. But this result says that the total influence is always large. Log n is a very, very non-trivial result. And you can also prove the converse, which says that if the influence is small, let's say smaller than a constant, then, well, this follows from here, then the smoothing system is determined by a few guys. There's a junta. Okay? This is called functions that sets that only depend on a small number of variables is called a junta in this literature. Okay? Because now there's a small subset of us who will decide the voting, the rest doesn't matter. Okay? So what this basically means that if the total influence is small, then we can approximate the set by changing it only a little bit, which will become a junta. Okay? So it's very close to a junta. Okay? So this is, I find this already very nice, but this has some really fascinating consequences about threshold phenomena. So the theory of phase transitions. So consider now a monotone set. Okay? So we have a monotone subset of the hypercube, and now take a random point in the hypercube, but now the distribution is not uniform, but it's a product distribution, right? So the probability that the ith component equals 1 equals now p, and that it's minus 1 is 1 minus p. Okay, so now this is everybody flips a biased coin, right? Now if this is a monotone set, right? So by monotone I mean that there are various ways of saying this. For example, you can look at the indicator function that x is in A. So this is a monotone function of each coordinate. That's one way of defining it. Another way is that if somebody changes a vote from -1 to 1, then this can only increase. Okay, so that's one. So we have a monotone set. Then, of course, and then we want to look at what's the probability of this. Okay? So clearly, when p equals 0, so this is p here, and here I'm looking at the probability under the distribution, under this product distribution of this set. Okay? If p is 0, then because of this set is monotone, this probability will be equal to 0. Well, unless A is the whole set. Okay? So this will be 0. And when p equals 1, then we will be in the set for sure. Okay? So now the question is, and this is a strictly monotone differentiable, infinitely many times different. It's a polynomial. So this function, we want to understand how this will go. Okay? All right. So this is an increasing function. There's a critical value. This is called PC, where the value of the function, where the probability equals exactly 1/2. Okay, this is called the critical probability. And the threshold width is now, I look at at what point the value of this probability equals epsilon. This is p sub epsilon. And I look at when it's 1 minus epsilon. So this is p 1 minus epsilon. The threshold width is the length of this interval. Okay? So now I want to know how fast, when I increase the probabilities, how fast will this grow from epsilon to 1 minus epsilon. This is called the threshold width. Okay? All right. For example, for the dictatorship, the probability that the outcome is 1, it's just equals p, right? Right? This is for the dictatorship. This is just what's the probability that it's only my vote that counts. So what's the probability that I vote? 1, well, that equals p. So we have this. So the threshold width is just 1 minus 2 epsilon. This is a very slow transition. Okay? But if I look at the majority vote, then it will look like this. There's a very narrow transition. So Herding's inequality tells you that the width here is of the order of 1 over root n. Okay? There's a very sharp transition from very, very small probabilities to huge probabilities. Okay? Clearly, the critical value here is 1/2. If everybody votes with probability 1/2, then the probability of outcome is 1/2. But if the probability that we use for voting is just slightly larger than 1/2, then boom, the outcome is almost surely 1. It's a huge probability. Okay? So there's a sharp transition here. And the question is, for what kind of functions do we have this? Okay? What are the sets for which we have this kind of threshold phenomenon? That the transition is abrupt. There's a phase transition. Okay? That's what we want. Okay. So the key for this is Rousseau's lemma. This is a lemma that was defined in that was used first in percolation theory. And what it says is that if I look at the derivative of this function, then the derivative is exactly the total influence. The total influence as we defined it here. The sum of these probabilities that we go in and out if the ith voter changes the vote. So this is really easy to prove. In a few lines you can prove it. The derivative of this function equals the influence. Okay, so let's see. But we have some results about the influence. This is Kankale linear result. It says that the influence, when the probability of the set is large, is a constant, then this influence is large. So what does this mean? It means that the derivative of this curve is large whenever we are near the critical value. How can this be large? Well, this can only be large if the transition is sharp. So the Kankale linear theorem implies that if the set is such that is symmetric in this weak sense, that all the influences are the same, then we have a sharp threshold. Then the threshold width goes to 0 as n goes to infinity. This is at least of the order of, this is at most 1 over log n. this is not, of course, log n is a small number, but it goes to infinity. In the case of a majority, we had a much sharper transition. It's 1 over square root of n. But this you cannot hope. In fact, there are this is sharp, so you cannot improve on this. Okay? But it's a beautiful. I think it's a beautiful and surprising result that tells you that no matter what set you have, and this set can be something like a graph property. You can have a random graph, and you can ask questions like, let's say A is the set when the number of edges is something, or if there's a clique of a certain size, or if there's a connected component of a certain size. Or you can come up with properties like this that are symmetric in the edges. So we have all these influences that are the same. No matter how such a property you come up with, it will always have a sharp threshold. As you increase the probability, this change will be very good. And you can prove this. Basically, I showed you the proof. The filling in the details is really not much. In 2-3 pages, you can do this. And we just use the log Sobolev inequality for the indicator function. Then you can get the Kankale linear result. And Russo's lemma is also there. So I think that's all I wanted to tell you. Here are some pointers to the literature in concentration inequality. There's, of course, a huge literature. There are some books on this. So Michel Ledoux wrote a book about 10 years ago, The Concentration of Measured Phenomenon. This is a very mathy book. So it has a lot of geometry and the isogeometric point of view. And Dupashi and Panconesi wrote a book which is much more for computer scientists with lots of nice examples. Here, the emphasis is on the analysis of randomized algorithms, and there's a book that's coming out soon that should be done in the near future. Let's say this year should be out, if everything goes well. Any question? Okay, so I think we can get ready for the karaoke.